Okay, so in this video we want to have a look at the idea of independent events, and this came up in an earlier video, coincidentally. And sometimes it is possible to sort of think quite intuitively about whether two events are independent, but I must say that that's very rare, and what we're really looking for here is genuine mathematical independence. So you need to be able to justify that according to this mathematical definition of independence, whether or not the events are or are not independent. Okay, so two events are mathematically independent if the occurrence of one event does not affect the probability of the other event. So technically, this is when the probability of A is the same as the probability of A given B. So, i.e., it actually doesn't really matter that B happened, the probabilities are still the same. This would also be, interestingly, the same as the probability of A given B didn't happen. The point is, it doesn't matter whether or not B happened, it's just the probability of A. That's technically at the core of independence what it's about. There are other formulas we can generate from that idea that help us to assess whether or not things are independent, and we'll look at those as we work through here. So first example, let's consider the Venn diagram opposite. Let's calculate the probability of A and the probability of A given B, and hence, so using what we learned from part A, determine whether events A and B are independent. Okay, so the probability of A, so there are 7 things in A out of 10 things in total. So it is 7 out of 10, or 0.7 if we want it as a decimal, same thing, doesn't matter. And probability of A given B, so given B, given we're one of those 5 people, what's the probability we're in A? So it's 2 out of 5, which is the same as 4 out of 10, so 0.4. So therefore, since the probability of A does not equal the probability of A given B, it seems that B does have an impact on whether or not A happens. So that means the events are not independent. So therefore you could say that they are dependent, but we probably tend to say that whether or not they are independent, particularly given the framing of the question. Determine whether events A and B are independent, events A and B are not independent. But it would be correct to say that that means that they're dependent. Okay, example 2, consider the Venn diagram opposite, calculate the following probabilities. Okay, so the probability of A, there's 6 things in A out of 10 things. So 6 out of 10, which is 3/5 or 0.6. Probability of A given B. Okay, so given that we're in B, the probability that we are in A is 2 out of 3, which is 0.6 recurring, okay, but they're still not quite the same thing. I think my original intent here was that this one might have been, but anyway, that's okay, they're actually not. Hence determine whether events A and B are independent. So since the probability of A does not equal the probability of A given B, events are not independent. Sorry, I think I intended for one of those examples to show you independence, but that's okay. One of the key things, students often mix up independence with the idea of mutually exclusive. So remember, mutually exclusive would be if there was nothing in the intersection. That's not the case at all. It is perfectly possible for, those are just two completely different things, okay? The intersection is about whether something can be both A and B at the same time. Independence is about cause, it's about whether, B causes the probability of A to change or not. So they're actually very different ideas. Okay, so it can be difficult to quickly identify independence in a Venn diagram, but it can be clearly seen in tree diagrams. So if we look at the situation where 2 marbles are selected from a jar containing 2 aqua marbles, which is A, and 3 blue marbles, which is B, the tree diagrams below show the situation if the selection is made with replacement and also if it's made without replacement. So if we replace the marble, there's a 2/5 chance of choosing an aqua marble at the first selection and a 3/5 chance of choosing a blue at the second selection. If we replace the marble, there's still a 2/5 chance and a 3/5 chance, and still a 2/5 chance and a 3/5 chance. So what we're seeing here is if we have independence, these probabilities and hence also these probabilities should be the same. because what that's saying is that the probability that A happens given that A happened is the same as the probability of A happening given that B happened, and therefore it's just the probability of A, essentially. Okay, so if you've got the same probability happening at that second stage, then you have independence. Okay. However, when we have with replacement, we know that the probability of the selections at the second stage change depending on what happens at the first stages. So by definition, there's not independence there. And that is illustrated by the fact that these probabilities, and hence also these probabilities, are not the same. And so we don't have independence. Okay, so the sentences there just talk through what I talked through. So we can consider independence in tree diagrams more generally. So events A and B will be independent if this probability is the same as this probability. So if the probability of A given B is the same as the probability of A given not B, which is the same as saying that the probability of A given B is equal to the probability of A. Okay, and it's also equal to the probability of A given not B. Those three things are all the same. Okay, so as long as these two things are the same, then and also these two things, that's implied, then we have independence. So if we recall the formula for conditional probability, it's the probability of A given B is equal to the probability of A divided by the probability of B. And this can be rearranged simply by multiplying by B to give this formula, which is actually called the multiplication rule for probability. Probability of A intersection B is probability of A given B times the probability of B. But if we have independence, we know that the probability of A given B is just the probability of A. So that becomes this. So this can be another way to check for independence. If events A and B are independent, then the probability of A intersection B will be the probability of A times the probability of B. Okay, and the reverse is true. If this relationship is true, that then tells us that the events are independent. Okay, so the converse is also true. Okay, so let's have a look at another example. A and B are independent events, and the probability of A is 0.6 and the probability of B is 0.7. Okay, so here we are told that they are independent events. Therefore, all our formulas to do with independence apply. So if they are independent events, that means the probability of A given B is just the same as the probability of A, which means it is 0.6. If they are independent events, it means the probability of A intersection B is the probability of A times the probability of B, which is 0.6 times 0.7, so 0.42. And then if they are independent, we can use the answers we've found here. We want the probability of the union, which we know is the probability of A plus the probability of B. So it's the addition formula for probability. This doesn't change for independence, but the point is that that probability was related to the independence. So probability of A is 0.6, probability of B is 0.7, minus the probability of A intersection B, which is 0.42. So that is, it's 1.3 minus 0.42. What's that going to be? Minus 1.2, so 0.88. Okay, example 4. Of the patients reporting to a doctor's surgery, 80% have fever, 50% have headaches, and 40% have both symptoms. Are the events having a fever and having a headache independent? Justify your answer. Okay, so again, we want to organise our information so that we can then calculate the relevant probabilities to determine whether or not we have independence. Okay. Alright, so we essentially have a patient can have fever or not fever. Now we could use a Venn diagram as well. I prefer the probability table or Carnot map just because it allows me room for the totals, and I've been given some totals here, which is why I went with this. I'm going to use decimals rather than percentages in my table is the norm. So we can have fever or not a fever, we can have a headache or not a headache. Okay, and our numbers are going to be probability, so they're all going to add to 1 in the bottom right. 80% have fever, so 0.8, which means 20% don't have fever. 50% have headaches, which means 50% don't have a headache. 40% have both a headache and a fever. So from there we can fill in the rest of the table. 40%, 10%, 10%. Are events having a fever and having a headache independent? Okay, so what I'm going to check is I'm going to work out independently the probability of having a fever and a headache is 0.4. That's just given in the table. The probability of having a fever times the probability of having a headache is 0.8 times 0.5, which is equal to 0.4. So therefore, since the probability of fever and headache is equal to the probability of fever times the probability of headache, fever and headache are independent events. Now this is one of those examples where I said it's not about you intuiting, oh, people with headaches are more likely to have fevers or vice versa. It's not about you bringing in your real world understanding of fevers and headaches. It is about what do the numbers in this particular context tell you. And in this particular context, there is mathematical independence between these two events. Now, it would only take that, on a different day, 51% of people have a headache and all of a sudden you don't have independence. Okay, so for this particular set of data, there is independence between fever and headache. Okay. So obviously if we were wanting to make a generalized statement about independence, you would be wanting to look at, these statistics for a much larger population of people rather than at one particular doctor's surgery on one particular day, potentially. Okay, example 5, the final one. A family owns 2 cars, A and B. Car A is used 65% of the time, car B is used 74% of the time, and at least one of the cars is used 97% of the time. Determine whether 2 cars are used independently. Okay, so again, I'm going to think about, okay, car A is being used or not used. Car B can be used or not used. Total probabilities of 1. Okay. Car A is used 65% of the time, so 0.65, so it means 35% of the time it's not being used. Car B is used 74% of the time, which means 26% of the time it's not being used. 97% of the time at least one of the cars is being used, so that's about the union, which means that 3% of the time neither of the cars are being used. Again, we can fill out the rest of the table from that information, so that's 0.23 there, that's 0.32 there, and then that must be 0.42. Yep, that all adds up in both directions. Okay, again, let's think about the probability of car A and B being used is 0.42. You've got that straight in the table. The probability of A being used times the probability of B being used is 0.65 times 0.74. Let me calculate that. Which is 0.481. And so therefore, since the probability of A and B is not equal to the probability of A times the probability of B, A and B are not independent events. Didn't give you many examples here where they are. My apologies. Are not independent events. Again, it would only take slight changes in the number to get independence happening. So you are looking to check this. Now, again, just in terms of setting out this work, you don't want to start by assuming that probability of A given B equals probability of A times probability of B, and then put your numbers in and say, well, this is 0.42, and this is 0.65, and this is 0.74, because these aren't equal. You're trying to test whether they're equal. So you want to calculate those two things separately, and then draw a conclusion from whether or not those two things are the same. Again, the other alternative is that you can look at the conditional probability. It depends on the information you've got. So you could calculate the probability of A and the probability of A given B, and again, draw a conclusion about if they are the same, you have independence. If they are not the same, you don't have independence. Okay, so just be careful about how you go about sort of setting out your answers there. Okay, so the work today, and this is the end of the work for probability, is from exercise 8G in your textbook.